In this video, we're going to begin our discussion on Chapter 4. So your book calls it, I believe it's something along the lines of numerical descriptive statistics. I prefer to call it common statistical measures. So the focus of this chapter is those very basic, very widely used statistical measures that we're going to need to calculate and to be familiar with as we progress through the study of statistics. In this video, we're going to focus on one of the three types of measures we're going to be looking at in this chapter, and that is measures of location. So we're going to be looking at measures of location in this video. But before we do that, we need to talk a little bit about mathematical notation. So just so everyone is on the same page and we know what's happening when I start putting formulas up, we're just going to throw down a couple basic things that you may or may not be familiar with. All right, so this first one, we're going to be talking about our variables and how we notate our variables. So this one is going to come into play a little bit more when we get into future chapters. Right, but whenever we see kind of a capital X or an uppercase X, right, that is representing our variable as a whole. All right, so if what we are looking at, the variable that we are interested in, is someone's hourly wage, for instance, then we could say X equals hourly wage, the variable as a whole. So that way when we need to incorporate that idea of saying this is our variable, we can just write X instead of writing out hourly wage, or if it's a variable with an even longer kind of name or descriptor, we can condense that and save some space. Right? But that is how we notate that overall, right, or the overarching variable, the variable as a whole. Now, when it comes to individual kind of observations for a given variable, we are going to use X as well, but in this case, we're going to use a lowercase x. Right, and it's usually going to be written as xi, X with a subscript I. Right, so what xi is, as I said before, it's the individual observations of our variable, but specifically, right, we're kind of notating which observation. So this I is a placeholder, right? It's really just kind of a placeholder for which observation. So xi is the ith observation. All right, so xi is the ith observation of random variable x. All right, so rv, random variable, I'm gonna be using that quite a bit. So rv is random variable. All right, so once we are actually kind of specifying which one, if we had x1, that would be the first observation, right? If we had x23, that would be the 23rd observation of our random variable x. All right, so on and so forth. All right, the next thing that we have is a operator. So this is uppercase sigma, the Greek letter sigma. Looks like a bit of a weird looking E, and it is the summation symbol. All right, so the summation symbol is just telling us that whatever's in front of that summation symbol, following the order of operations, we just need to add up all of those. All right, so the most common way you're going to see this, especially as we get started, is going to be as follows. this is well, I guess really this is just an example of how it would look. Right, I've added some things here. Most of the time in this class, we're just going to use this version that I first wrote down. That's just looks like the little E. But technically, it should look like this if we're being as accurate as possible. So what this is saying, right? So here we've got at the bottom I equals 1. Then we have our summation symbol, and then we have n. Right? N is the size of what we're looking at, right? In this case, I'll write this down in a second. Lowercase n is the sample size, right? But ultimately, the main point right now is that n is just how many observations do we have, right? It's the number of observations. So when we have the sum from I equals 1 to n of xi, that's telling us that we're going to add up all of the observations of our random variable from the first to the nth observation. So we would start with, obviously, the first one, x1 plus x2, all the way to the nth or the last observation. Right? So that is what that summation symbol is telling us to do, is just to add up all of those values. Right? So again, we're usually not going to be using these pieces up here, the I equals 1 and the n. Those are just going to be implied, right? But those are there, and that is what it's telling us to do. Right? Once we get out of the generic formula version, right, these will be actual numbers, and so you will just be adding them up. All right, after that, we'll go ahead and talk a little bit about the differences between populations and samples. All right, so for most of the things, or maybe not most, but for a lot of the things that we're going to be looking at in this chapter, even if we're not using a different formula, we're going to notate the measures for samples and populations differently, right? So the statistic, the sample statistic, is going to have a different symbol, right, notating it, right, or kind of identifying it than the population parameters. So as a rule of thumb, if the symbol is a Greek symbol, so a letter from the Greek alphabet, that is indicating that we are dealing with a population parameter. We're going to see an example of this in just a minute, so if you're not 100% sure, but so things like alpha, beta, sigma, so on and so forth. It's the Greek alphabet, right? If it is notated using the Latin alphabet, so our alphabet, A, B, C, D, so on, and so y'all know the alphabet, then it is a statistic, right? That's how we represent the statistics, right? And then similar to this, but not wholly, if we have a capital N, if we have a capital N, that is the population size, right? So if we're dealing with a parameter, if we're calculating a parameter, we're going to have N as our population size, and then if we're calculating a statistic, we're going to have lowercase n as our sample size. All right, now functionally, it doesn't really make a difference, but notation-wise, it is important that we identify whether we're talking about a population or a sample. All right, so functionally, the kind of number of observations, that's not going to, whether it's a population or a sample, it's not going to make a difference in how you calculate things, but notation-wise, it is important. All Right, so I believe those are the big things that we need to look at. I'm sure I forgot something, and if/when we come to that, we will look at, we'll go over that in some detail. All right, so what we are going to be looking at in this video are measures of central location. All right, so measures of central location, what we're trying to get with these, so these are descriptive statistics. They're meant to help us describe our data set. Right, and with the central location, that's exactly what we're trying to do. We're trying to figure out where is our data centered around, right? If we imagine a number line, right, stretching from negative infinity to positive infinity, right, where on that number line does our data lie, right? Where is it centered around at the very least? Where's the central point, right? And that's going to be important because depending on which one we're looking at, we might expect to see more or less values at that central location, right? Depending on the distribution of the data and several other factors. But we're not going to get into that, but we are going to be interested in this. All right, so let's go ahead and start looking at some of these measures. All right, a lot of these are going to be very familiar to you, I would imagine, some of them more so than others, but let's just go ahead and get started. We're going to first start with the mean. Specifically, there are a couple different types of means. So specifically, we're going to start with the arithmetic mean. So actually, I probably need just to do the whole board for this. Right, so the arithmetic mean is just what we more commonly refer to as a mean or an average. Right, so if you've ever calculated an average, then you have calculated the arithmetic mean, assuming you did it correctly. But this is the kind of the most commonly used of our measures of location. We're going to use this one a lot more than most of the other. Actually, really, we're going to definitely use this one more than any of the others in this section. It is very important, and it's relatively simple. It's got a lot of great properties, right? And for that reason, most of the time, once we move past this section of material, whenever I ask for the mean, I'm asking for the arithmetic mean. All right, so we've got a couple others that we're going to talk about. I will specify if I want one of those. If I just say the mean, I'm looking for the arithmetic mean. Now, there are two types of arithmetic means. We have the population mean, so this is where we're going to start splitting up between population and samples. All right, so population mean, so this would be the parameter. And we're going to calculate, right, and this is the, I guess, really the formula for the population mean is as follows, right? Mu, right, so this is the Greek symbol mu. So again, this is a parameter, so we're going to be notating it with a Greek letter. So mu equals the sum of xi divided by capital N. So population mean equals the sum of all of our xi, so just add up all of our variables and divide by the total number of observations that we have. All right. So pretty simple. If we've done a mean before, that should seem pretty familiar. All right, but that is our population mean. We also have the sample mean. The sample mean is going to be notated as x bar. Right, because it has a little line over it. So we've got the X, the Latin alphabet, all right, and then it's a little different in that it has this bar over it. All right, so X bar equals the sum of Xi over lowercase n. So we're going to add up all the observations for our variable, then we're going to divide by the sample size. So functionally, the formula for the population mean and the sample mean are the same. You just add up all of the data that you have, divide by however many observations you have. Right, however, if you are dealing with a sample, you need to notate it as X bar. If you're dealing with population data, you need to notate it as mu. I will be a stickler about this. So in, let's say, a word problem, it might describe where the data comes from. You're going to need to be able to identify, is this population data or is this sample data, similar to what we were doing in kind of homework for chapter 1. All right, so we're going to be able to, I need to identify that. Sometimes I'll just tell you this is sample data or this is population data, but sometimes I'll ask you to determine that on your own. Right? If you don't notate it correctly, you'll lose some points on homeworks and tests, things of that nature. All right, but that is the sample mean. So I'm sure you all know how to, I would imagine most, if not all of you, are pretty comfortable taking an average, but just in case there's anyone that is not, we're just going to do a quick example of this. Let's say that in my class, actually this fake data that I made doesn't really lend itself well. Let's just skip the kind of example and just say, well, not the example, the scenario. Let's just say this is sample data. All right, in this case, I'm just going to tell you, it could be anything. And let's say that this is our data. All right, and what we have here is 28, 37, 81, 44, and 59. All right, so if we were asked to find the sample mean for this, really if we were just asked to find the mean, right, we would say, well, it's sample data, so we need to use X bar instead of mu. We need to add up all of our values, so 28 plus 37 plus 81 plus 44 plus 59, and then we're going to divide that by the total number of observations. So we look, we count, we see that there are 5 of these. So we have 249 over 5, which gives us a sample mean of 49.8. And that would be our sample mean. So again, relatively simple, but again, very useful. We're going to be seeing the sample mean a lot. We're going to be seeing the arithmetic mean a lot. Specifically, we're going to be looking at the sample mean more so than the population mean. We're not going to get into why right now, but it will become clear later in this semester. All right, but that is the arithmetic mean. We want to make sure that we know the difference between our population data and our sample data so that we make sure that we notate it correctly. Other than that though, the actual process of finding the population mean and sample mean are identical. All right, the next type of measure of central location we're going to talk about is another type of mean known as the weighted mean. So what the weighted mean does that the arithmetic mean does not is that it allows us to put different weights on our observations. right? So with an arithmetic mean, all observations are weighted equally, right? They all count the same towards the end goal. But with a weighted mean, we can make some observations more important than others. Right, so a good example of where, well, actually, let me do the formula before I start talking about that. All right, yeah, I'll just go ahead and pop that up. I'm just going to use X bar. We don't really have a dedicated symbol for the weighted mean, right? But this is the formula for the weighted mean. So, the weighted mean is equal to the sum of xi times wi divided by the sum of wi. So, wi is the weight of the ith observation of x. So, each observation of x is going to have its own weight. So, there's x1, w1, those are paired together. So, w1 is the weight of the first observation of x, so the weight of x1, right? And when we are doing this, you'll notice that the brackets, right, go around. We have these brackets around xi times yi. That's telling us that we need to do this multiplication before we do the sum, right? So kind of our orders of operation, right? It's in these parentheses. We need to multiply each x by its corresponding w. Once we have done that for all of our observations, then we will add them up and divide by the sum of our wi's. All right, so let's take a look at this in practice. All right, so one of the places that I personally see this most commonly, these weighted means, is in my grade book. All right, so your final grade is going to be a weighted average, right? If you look through the syllabus, which hopefully you have, you will see that there are different assignments, right? Different assignment types that have weights to them. Alright, so if we look at the syllabus, we can go and see that your homework average is going to be 20% of your final grade. The first and second test are going to be 25% each, and then the final is going to be 30% of your grade. So, let's say that for your homework average, you have an 87. For your first test, you got a 93, congratulations. Then for test 2, maybe you felt really confident about test 1, right? So you did well on it, so you're feeling confident in the course. Also, test 2 is just hard. It is a difficult test, I'll go ahead and tell you that. It's just a difficult section, and let's say you get a 71 on that. And then for the final, you get a 79. Alright, so with this information, we can calculate our weighted average. Alright, so I'll leave that up for a second. I'm going to need to erase it to be able to actually show this on the board. Although I suppose y'all can just pause the video and write this stuff down whenever you want to. Alright, but so there we go. Alright, so when we go to do this, alright, try to give myself a good bit of space. So up top, this is where we are multiplying our x's and w's, right, and then adding them together. So the first pair we have is 20% for the homework average and the 87. Is that what it said? Yes, 87. When you're doing this on your own, You don't really need to put the percentage in here. You can just put 20 in. If you do put the percentage in, depending on your calculator, it can mess some things up. Also, at the end, those are going to cancel out, so it doesn't matter anyways. All right, but 20, and actually, I'm gonna leave those out myself because I'm gonna run out of space. I can already tell. Really overconfident with that 20 times 87. All right, so no, that's not gonna cut it. We're gonna have to change that. There we go. Sorry about that. All right, so again, up in the numerator, we've got the sum of our xi's times yi's, or excuse me, xi times wi. So, well, we've got them here, and I flipped them around. That's okay. They can be in different order, right? But we're going to, the important thing is that we're multiplying each pair, right? Each weight and xi, so each xi and wi pairing, we're multiplying those together first, and then we're adding them all together. Then in the numerator, we're just adding all of those weights together. So once we actually do this calculation, right, punch that into our calculator, and I didn't actually write that down, did I? No, I did not. Well, I can just tell you what it is. So we would get 800, or we would get 8,210 over 100, all right, which would give us an average of 82.1. All right, so there we have that weighted average. That is how we would calculate it. All right, now one of the good things about the weighted average is that the weights don't actually have to add up to anything specific. Here in this instance, they do add up to 100 because I grade out of 100. But let's say that we didn't have that, right? We didn't have those weights. Let's say it's getting towards the end of the semester, you want to calculate what your current average is. We haven't taken the final yet. Right, if that were the case, all we would have to do is just not include those two things. We don't have the final yet, so we can't include it in the numerator, and then we just would not have that weight down here in the denominator, right? Everything else would be done just like we did, and I'll tell you that the final without, or excuse me, the final grade without the final would be an 83.4, so that way you can run through this on your own to see if you get that answer. Right, but that is a weighted mean. It's not going to be seen as commonly as the arithmetic mean, but still is used relatively frequently by myself in particular. All right, we have one last type of mean to go over, and that is what's known as a trimmed mean. All right, so the trimmed mean is a little bit more involved than the other two, right? But it is a version of the arithmetic mean. So it's an arithmetic mean with an equal proportion of the highest and lowest values trimmed off or cut off. So when we are doing this, we're gonna have to do a little bit more work. Not a whole lot more work than what we had to do with the arithmetic mean, but a little bit. All right, so I'm gonna go ahead and put some data up here before we get into it. So when we're doing something like a weighted mean, when we're doing something like a arithmetic mean, it doesn't matter if our data is sorted or not. We don't have to have it in any particular order. But when we are doing a trimmed mean, we do need to have it in order, and we need to have it in order from lowest to highest. So I'm going to go ahead, just because you don't want to see me write down a bunch of numbers and then put them in ascending order. I'm just going to write them down in order, but just know that that's not a given. So it's not given that the numbers are in order, so don't just start working on a problem assuming those numbers are in order if it's important, right? If it's important for them to be in order, you want to check and look and see if they are in order. If not, you need to order them yourself. All right. So here we've got our little data set. So when we are doing a trimmed mean, we're going to put this data in order. And when we're asked to do this, we're going to be asked for a particular trimmed mean. And by that, I mean we're going to be asked for a certain percentage of a trimmed mean. So it's going to be in the format of calculate a X% trimmed mean. So that could be a 5% trimmed mean, 10%, 15, 20, 17.5% trimmed mean, whatever is actually being asked for. All right, so what we're going to do, I'm just going to go through this this process by just showing you how this is done, because otherwise it gets a little confusing. We're going to do a 20% trimmed mean. All right, so when we're doing a trimmed mean, right, the first thing we need to do is make sure our data is in order. The next thing that we need to do is figure out how many values we need to trim, all right? So whatever percentage trimmed mean we're doing, that is how much data we need to take off from the top and the bottom, right? And so we need to say, well, how much of this data is 20%. So we would need to, one, know how much data we have. In this case, our sample size is 12. So we need to know what 20% of 12 is. All right, so we can just take 12, multiply it by 0.2. All right, that's gonna give us 2.4. All right, so we need to trim at least, right, at least 2.4 numbers from the highest and lowest values, right? But we can't trim 2.4 values, all right? We can't trim 0.4 of a number off. So we're gonna need to round up to 3, all right? So we're always gonna round up. So normal rounding rules don't apply in this case, right? So even though we've got 2.4, we're still rounding up to 3 because we have to trim at least 2.4 values. All right, so we have, so we round up to 3. We're gonna trim those values. So I'm going to leave these up here, but I'll run a line through here. So again, we're trimming. You don't have to draw the scissors, but it is fun in my opinion. Right? So we're going to cut the 3 lowest values and the 3 highest values. All right. Once we've done that, we are simply doing an arithmetic mean. So that's the hard part. That's the part that takes a little bit more work. Once we do that, we're just going to take the values, right, the numbers that we have left, and calculate an arithmetic mean with them. All right, so we would just add up 59, and I'm not going to do it down here just because I'm running out of space, but 59 plus 62 plus 66 plus 71 plus 73 plus 79, and that is going to give us 410 divided by the number of observations we have, and this is just the ones that we have left and just the ones that we're still using. All right, and so we have 6 of those, not 0. So we get 410 divided by 6. And I'm going to just erase this and write down the actual answer, which is going to give us a trimmed mean of 68.33. Right? But that is how we do a trimmed mean. So again, we need to put our data in order. All right, we need to order our data. Right, we then need to figure out how many values we need to trim from the lowest and highest values. Right, so we do that by taking whatever percentage trimmed mean we're working with, right, figuring out what that percentage of our sample size is. If we don't get a whole number, we need to round up. We always round up. Then we're going to remove that number of values. In this case, it was 3. All right, we rounded up from 2.4 to 3. Taking the 3 values that are the highest and the lowest, right, removing those, and then taking a arithmetic mean with what's left. All right, but that is how we do our trimmed means. All right, so that is it for our means. Now we're going to get into some things that you're definitely going to, or I would assume you're familiar with, right? So most of the time, especially kind of in grade school when you probably first heard about means, they also introduce 2 other topics, right? So you often hear mean, median, and mode, right? So mean is a measure of central location, as are the median and the mode. So our median is simply the data value in the middle of an ordered array or an ordered data set. Alright, so again, ordered array, that's just our data is on order, right? We put it from highest to lowest or what have you. Alright, the mode is the most frequently occurring value. That most frequently occurring value. All right, so I'm not going to write the data back up here, but let's just use the data that we use for that 20% trimmed mean to look at the idea of the median. So when we look at that data set, we have 12 pieces of data, right? And so when we have an even number of observations, then we are going to have, we're not going to have a direct middle of our ordered array. There's not going to be one number that's exactly in the middle. right? So when we have that occur, right, we are going to, actually I'm going to just write this data back up here. Why not? Actually, no, I'm not. That's ridiculous. That's going to take too much time. All right, so we're not going to have one value right in the middle, right? So when we have an even number of observations, we average the numbers that are the two numbers that are in the middle. All right, so in this case, the two numbers that are in the middle, so the 6th and 7th values are 66 and 71. Right, so we average those two numbers to get our median, and we find that we have a median of 68.5. The mode is just the most frequently occurring number. In this case, the most frequently occurring number for this previous data set that we used was 37. It was the only value that appeared more than once. All right, and so we have 37 as our mode. All right, so when we're looking at the mode, we can have more than one. All right, so if we have two numbers that appear most frequently, so let's say that they occur 3 times each, and that's the highest out of any of the other ones. All right, we can have 2 or more modes. All right, so we can have more than one mode. There's really no cap on that. And if you have a data set where each number is only appearing once, then technically they are all the mode because they all appear most frequently, right? All right, but that is our median and our mode, all right? So before we end, all right, so those are all of the measures, right? So those are all of those measures of central location, right, that we're going to discuss in this video. So we've got our means, so we've got our arithmetic mean, both the population and the sample. We also have the weighted mean and the trimmed mean, and then we have our median and our mode. All right, so one question we might be asking is, why do we have so many different measures of central location? All right, the reason for this is kind of twofold. All right, one is because not all data is going to be appropriate for all of those different measures. Right, so when we are looking at our different levels of measurement, right, these are going to determine which one, or help determine which one we're using. Right, so if we look at, say, the arithmetic mean and the trimmed mean, right, it's not going to be appropriate to use nominal or ordinal data, right? In fact, we simply can't use nominal or ordinal data because we can't, this is categorical data, we can't do math with categorical data, right? So if we're trying to find an arithmetic mean or a trimmed mean, right, it has to be the case that we have either interval or ratio level data. Right? If we're dealing with the median, right, we have to find the midpoint of an ordered array, right? So we can't use nominal data because we can't put it into order, right? However, we can put it into order if we have ordinal data. So ordinal data can be put into order, right? That's really the only thing that we need to be able to find the median, right? And then of course, if we have interval or ratio level data, we can still find the the median, right? Because we can still put that data into order. For the mode, this one we can use at any time, all right? So for any of our different levels of measurement, all we need to know is to be able to find out which one's the most frequently observed, right? That kind of harkens back to the frequency, right? The frequency distributions, right? And we can do those with nominal data, ordinal data, interval, or ratio. All right, so again, the big thing is that, so the mode, we can use any of these different levels of measurement. Any of those are appropriate to use the mode for. We can only use the median if we have ordinal, interval, or ratio scale data. And we can only use the means, all right, arithmetic or trend, if we have interval or ratio data. All right, so that's one reason that we have so many different measures of location. Another one is tied to the concept of resistance. All right, so a measure is resistant. I'll go ahead. All right, a measure is resistant if it is not overly affected by outliers. All right, we're not going to get too bogged down into what outliers are in this video. We'll discuss those a little bit more in one of the videos for next week. But an outlier, just the long and short of it, is a value that is relatively large or small compared to the rest of the data. All right, so if we have outliers, right, and we have a measure that is not resistant, right, those outliers, those relatively small or large values, can pull, right, our measure, right, to where it's not necessarily as representative as maybe we would like it to be. Right? If we have a resistant measure, it's going to resist the pull of those outliers. Right, so the arithmetic mean is not resistant, right? So I was going to show you this with something else, but honestly it wasn't as, it didn't really show it as well, so we're just going to do something from scratch. All right, so I'm just going to write some data out here. Actually, I'm gonna just go ahead and change this data because all right, so let's go with this. We'll see if this actually gives me what I'm looking for. All right, so if we were to calculate our sample mean, all right, so just quickly calculate our sample mean for this. All right, so we just add up all of these values, so 10 plus 178 plus 199 plus 208 plus 237, that gives us 832. We're going to divide that by 5. All right, and we're going to get 166.4. All right, so we're trying to get an idea of the central location. All right, so with this 166.4, all right, you look at it, you can compare it to our data. All right, well, that's in between 10 and 178, right? So you've got one value to the, I guess, the left of it, and 4 values to the right. So you could question, hey, maybe this isn't the most kind of representative measure of central location. All right, now let's say that we did a 20% trimmed mean. All right, and I'm gonna pretty much fly through this, right? But if we're doing a 20% trimmed mean, right, our data is already in order. We need to know how much 20% of our data is. All right, we have 5 observations. 20% of 5 is just gonna be 1. All right, so we don't need to, we've got a whole number, we don't need to round. All right, so we are going to be cutting the highest and lowest value, right? So we would be cutting the 10 and the 237. So we get 585 divided by 3 because we only have 3 values left for a 20% trimmed mean of 195, right? That looks like that's closer to being in the middle of this data set, right? We can even also find our median, right? So if we look for the median, that's the value in the middle, right? Well, this is a pretty small data set. It's easy to see that 199 is in the middle, right? We've got 2 values to the left of it, 2 to the right. So 199 is our median, right? So that's dead in the center, right? So this is kind of the idea of resistance, right? So we have this, all right, potential outlier in 10. 10 is relatively small, all right, or is small relative to the rest of our data set, right? In the high 100s and in the low 200s, right? That is, that data is much larger than this small kind of outlier. So that 10 pulls down our arithmetic mean, it pulls down our average when we're using the arithmetic mean, right? But it doesn't do that with our trimmed mean because we're cutting out any potential outliers because those are going to be in the highest and in the lowest values. So if we cut those out, we're less likely to be affected by them. And then also for the median, it doesn't matter it doesn't matter if we have really high values or really low values in the extremes because we're always looking for that middle. All right, so the trimmed mean and the median, as well as the mode, are all resistant. Right, again, the mode's resistant because it doesn't matter if we have outliers. We're just looking for the most frequently observed value. Right, so the trimmed mean and the median are, the trimmed mean, the median, and the mode are resistant measures, right? But the arithmetic mean is not resistant, right? That's why you'll often see things like income or earnings reported in median, as a median, right? The median wage, the median income in the US instead of the average, because if we have, a couple hundred billionaires in our data set, right, that's probably gonna skew our data and not give us a representation of what we're actually trying to look at, right? So that is kind of the idea behind resistance, right? And that is it for our measures of central location. So in the next videos, we will be continuing to go through chapter 4. We will be looking at the other 2 types of measures. So the next one will be measures of dispersion, followed by measures of relative position, right? But those are for another video, and I will see you then.